I'm not quite done with the tests yet. I should have those back on Wednesday. And then I put up a weekly assignment. Did you see that? One thing about the weekly assignment. So weekly assignment 1. There's one of those questions. I don't remember which one. It talks about water at saturation. And on that one, you're going to have to use the tables. So go to the, in D2L, there's a tab in content. There's a tab that says tables. And then it has water saturation, indexed by temperature, indexed by pressure. And then it has, superheated steam, compressed liquid water. This is just at saturation, so you're just going to use those saturation tables indexed the way by what you're given, I think is pressure. Okay. Now we are getting into control volume analysis. Does anyone have any homework questions before I start this? Okay. So control volume analysis. And control volume analysis we'll use that when material is moving through a device. Okay. And the devices we're going to be dealing with are often going to be nozzles or diffusers, compressors and pumps, and I think there's one more. But so things where you can imagine like a nozzle, liquid is flowing in one side and flowing out the other side with different properties. And we will break this up into 2 different kinds of calculations. Mass balance. So that's just conservation of mass. And second, the first law of thermodynamics. And this is going to have to take a new form. So this is going to be the first law of thermodynamics for control volumes. And I'm going to start with the mass balance.
Are we still like doing the same things with those systems?
Yeah,
We're still concerned with
that's right. We're doing the same kind of calculations. It's just that now we don't have any way to trace to circle an amount of material and trace that over time. All we can do is look at the device itself and consider what's flowing in and what's flowing out. Okay, so I'm going to start with mass balance. And so if you have a device like this, And you have material flowing in and material flowing out. And then in here you have just material. The mass balance equation says the rate of change of mass inside the control volume, so dm dt inside the control volume, is equal to the rate at which material is flowing in minus the rate at which material is flowing out. Dm dt CV is the rate of change of mass inside the control volume m dot in is the rate of mass flow into the control volume, and m dot out is the rate of mass flow out of the control volume.
Is that CV like a subscript?
Yeah, it's a subscript. Yep. You're not multiplying that or anything. One formula that's going to be useful all the time and this is at inlets where the mass is coming in and exits. The formula is the rate of mass flow rate is equal to the area times the speed of the material going in the inlet or out the exit divided by the specific volume. So A is the area of the inlet or the exit. V is the average speed of material passing through the inlet or the exit. And lowercase v is the specific volume. And here's where that comes from. If you imagine so imagine your inlet or exit as like Play-Doh Fun Factory. Okay, so material is going through this aperture in this direction. This area is A. This length, we'll call that L. And at a given instant, the extruded mass that's come through there is the area times the length. Okay, that gives you the volume times the density of this material. Okay, so that's like, this is equal to the mass, the extruded mass. Okay, do you have to know this stuff? What I'm doing right here? You don't have to know this. If you want to just use that formula, it's fine. But I just want to point out that this formula is derived in a very simple way. It may help you sort of keep it in your head if you follow what's going on here. Okay, so what we want isn't the mass that's extruded. We want the rate of extruded mass. And so take the time derivative of that. M dot is the time derivative of A times L times the density. The only one of these that's changing in time is the length, right? That area is constant. The density, we're assuming it's a constant, one type of material. And so this comes out to be A times rho times dl dt. Well, dl dt is just the speed. The density is 1 over specific volume. The only reason we're changing the specific volume from density is because specific volume is something that's given in these property tables. So it's more convenient for us to use this. And so this comes out to be AV over little v.
So this example, you're just concerned with the outlet going out or the inlet going in.
Yeah, right. You do it the exact same way, but you do have to think about whether, it's important whether the material is coming in or leaving. But you could use this approach to calculate in this conservation of mass equation. You could use it to calculate m dot in or m dot out. Okay. One thing I want to point out about this is this is for Play-Doh, right? But gases and liquids don't behave exactly like Play-Doh. And in fact, like as a fluid is coming out of that aperture, it's not going to have a uniform distribution of speeds. Okay, and that's why I said that this is the average speed. So that's something you'd have to know, but that's not going to be a big deal in this class. When we talk about speeds, we're just always going to be talking about the average speed going in or out.
If we're doing a problem where it's like start to finish, like completely through the system, do those two areas have like a relationship, like PV to the N?
We don't know that. That would have to be something that was given to you, like by your engineers. Like, hey, Poindexter, go find out what for my crazy new machine, like find out an exponent relationship between P and volume, and then they'd come back and give you the note, and then you could use that in calculations. But you can't assume anything like that.
Yeah, like it would be provided.
Right.
I just wanted to see if that's even how it would work.
Yeah, I mean, you could work that into basically like the way all of these work is you have a bunch of equations that are applicable and you have a bunch of variables you're trying to find, and you're just trying to string together the right series of equations so you have the same number of variables as equations, so it's solvable, And so, yeah, if somebody told me to make a problem that used an exponent law like that with this, like, yeah, I'd have to count up my variables and then require just enough calculations that I could fit in this one more equation, you could make that fit in.
Got it.
Okay, let's see this in a couple example problems. If a tank can hold 20 kilograms of water, and it starts with 5 kilograms of water, and the rate of mass flow coming in is 2 kilograms per second, and the rate of mass flow out is 1.5 kilograms per second. Then first, how long in seconds until the tank is full? And second, if the average speed of water flowing in is 10 meters per second, and the average flowing out is 25 meters per second, and we're going to assume that this is liquid water. What are the areas of the inlet and the exit? Okay, well, we know that for part A, the rate of change of mass in the control volume is equal to m in dot minus m out dot. And so dm dt is equal to 2 minus 1.5. So it's equal to 0.5. And now I'm going to multiply both sides by dt, and we get that dm for the control volume is equal to 0.5 dt. And now we can integrate both sides from state 1 to state 2. And now we have to think about what the values are at state 1 and state 2. At the start of this problem, the mass is 5 kilograms. So our state 1 mass is 5. And at the end, the final state, the tank is full, so that's 20 kilograms. And over here, I mean, we might as well just start the stopwatch at the start of this motion just to make things less complicated. So we'll call this time equals 0. And then this one, we're trying to find this t. Okay, so I'm going to leave that as t. Really, if you're doing this in a math class, you should be careful that your variables, your dummy variables for the integration are different than your variable for the... so you see people do this pretty often with just t's everywhere. But really, this should be like, I guess maybe I would do it as like, we're trying to calculate this time tau, okay? And this is 0.5 dt. So this tau then is the time to fill the tank. Everyone with me on this? This is a really useful thing that you're going to want to get used to in this class, separation of variables, where you have a derivative and you just, this is another thing the math professors wouldn't really like, but it always works for well-behaved functions. So just multiply the dt to the other side. Then you have two things you can integrate and integrate both sides. And so this says the mass in the CV evaluated from 5 to 20 is equal to 0.5 t evaluated from 0 to tau. And so 20 minus 5 is equal to 0.5 tau. And so tau is equal to 30 seconds. Any questions about that? Okay, so now we're given speeds. We have something in those apertures that's measuring the speed of water flow. And we're just going to do one by one the inlet and the exit. So the mass flow rate coming in is A times the speed divided by the specific volume. And we know that the speed is, what did I say, 10 for the inlet? So we have 10A. And then the specific volume, that's something if you want to be really accurate about it and you know the rough temperature range that the water is at, you can go to the tables and look this up. If you're just going to say like, it's probably about room temperature and you're not too worried about tenths of a percent in precision and stuff like that, you can just say the density of water. So density of water at room temperature is about equal to 1,000 kilograms per cubic meter. So that means that the reciprocal of that is 0.001. You can always use that as a reasonably good approximation for liquid water. And this has to be equal to 2. And so the area is equal to 2 times 0.001 divided by 10. And so that area is 0.0002 meters squared.
Is that as small as it seems like, or is it?
Well, not really. I mean, that's, well, let's calculate so imagine it being a square. So the square root of 0.0002 is 0.014. So if that was a square, the side lengths would be 1.4 centimeters.
So no, it's not as small.
Yeah, it's not tiny. And then at the exit, m dot out is equal to AV over little v. This is going really fast. The speed is 25 meters per second. So 25A divided by 0.001 is equal to 1.5. And so A is equal to 1.5 times 0.001 divided by 25. And you get 6.0 times 10 to the minus 5 meters squared. And so that comes out to be about 0.8 centimeters if it's a square for a side length. Any questions about that? I would definitely give you the advice that when you see problems that are using conservation of mass balance equation, look for places where this, it's very common that you're going to use this equation for the mass flow rate.
I mean, is it ever not like linear like this?
It's linear like this because we're only dealing with the average speed. If it was dealing with like a distribution of speeds, like for example, if you have a, boy, can I draw this? Okay, so say you have a fluid. That's not a great picture, but if you have fluid coming out of an aperture like this, this shape gives you like a distribution of speeds that you're going to have. So, like the speed here would be this, here would be this. It's going to be fastest right at the middle like that. Okay, so it's a complicated shape anyways. Okay, and if you were going to try to take all of those speeds into account, then it would get messy, dealing with the speeds. But since we're just saying like, yeah, we're not messing with that, we're just saying somehow we already know the average speed, then that's why it's linear.
But if you were really trying to determine average speed, you'd have to.
Yeah, if you're trying to determine the average speed, yeah, it could be complicated. I mean,
it'd be like
depending on what information you're given.
fluid dynamics, right?
Yeah, right. The reason I know the shape of this is it comes from a simple, simplified version of the fluid dynamics equations. Yeah. Okay, let's do another one. So that was one where the material coming in and the material in the tank and the material leaving were all in the same phase. But that doesn't have to be the case. Your device could be taking something that was saturated liquid and turning it into a superheated vapor or whatever, So let's do an example now where we have to deal with different phases. So let's say we have a heater. At steady state. And at the inlet, We have a water vapor, steam, and the pressure. Oh, okay. We have two inlets for this, I guess. So we have an inlet 1, an inlet 2, and then we're going to have an exit. So inlet 1, it's a water vapor. I'll denote this with P inlet 1, so a double subscript. And we have a pressure of 7 bar, a temperature at inlet 1 of 200 degrees Celsius, and a mass flow rate at inlet 1 of 40 kilograms per second. And then at inlet 2, we have liquid water. That's also at a pressure of 7 bar. The temperature is 40 degrees Celsius. And we happen to know the area of this aperture is 25 times 10 to the minus 4th meters squared. And then at the exit, we have saturated liquid water. The pressure at the exit is 7 bar. The volumetric flow rate is 0.06 meters cubed per second. And we want to calculate the mass flow rate at inlet 2, the mass flow rate at the exit, and the speed going into inlet 2. Okay, so that's it. There's a couple of things that we need to make sense out of before we can get into the calculations. So volumetric flow rate. So that's like volume per time, okay? If you go back to the equation for mass flow rate, notice that what we have is a density times a volumetric flow rate. The area times the speed is telling you how much volume goes through per second. And then you're multiplying that by the density to get the amount of mass that flows through. So the volumetric flow rate in this case, how did I write that? Yeah, volumetric flow rate is equal to just A times V.
You can see that in the units too, because areas.
Yes, exactly. Yep. Yeah, the units can tell you a lot about stuff like this. Second, steady state. What does steady state mean? Well, remember, steady state means no properties change over time. mass is a property. And so this says that dm dt in the control volume is equal to 0. Okay, so our mass balance equation says dm dt in the control volume is equal to m dot at inlet 1 plus m dot at inlet 2 minus m at the exit dot. And let's see if we have the information we need to get the properties that we need for this. Well, mi1 dot, we already know what that is. That's given to us directly. And because it's steady state, this goes away. So let's just fill in what we know. We know that 0 is equal to 40 plus mi2 dot minus me dot. At inlet 2, we have liquid water. So if this is a liquid, if this is a compressed liquid, not at saturation, okay, do we have enough properties to look up values in a table? Yeah, remember, if you're at saturation, you need one property to look up values. If you're not at saturation, you need two properties to look up any other properties. So with this pressure and temperature, we should be able to look up, well, anything we want. What's the thing that we want here for inlet 2? What's going to be helpful to us?
Specific volume?
Yeah, specific volume, because we're given the area of that aperture, and so let's see. We should be able to. Let's see, can we calculate that yet? Not quite. But we know we're looking for the, oh, well, we're looking for m dot. We don't have a speed there yet. We have an area. Okay, well, yeah, we know we can look up specific volume. It seems like that's going to be helpful. So that's at inlet 2. What can we look up at inlet 1? Well, we have the mass flow rate. We could look up anything we want. I'm not sure that we're going to need anything there. And then, do we have what we need to look things up at the exit? Yeah, because it's saturated, so you only need one property to look that up. So this is because we have two properties. We can look up VE in a table. And that's because we have one property at saturation. So let's first go to the exit. We have the volumetric flow rate. Second. Okay, so at the exit, we have that the volumetric flow rate is 0.06. And that's equal to the area times the speed divided by the specific volume. And we can look up the specific volume. So from the saturated water table,
Isn't that 106 just equal to 80?
Yeah, I was looking at that too.
oh, you're right. You're right. Thank you. Okay, so we got that. Well, what we can do now is we can figure out the mass flow rate from this. So, yeah, if we look up from the saturated water table, specific volume at the exit is 1.108 times 10 to the minus third. And so the mass flow rate at the exit is equal to, the density times the volumetric flow rate, which is the volumetric flow rate divided by the specific volume. And so that gives you 54.15 kilograms per second. Bless you. Okay, now that we have the mass flow rate at the exit, we can plug it into this equation. We have 0 is equal to 40 plus m dot at inlet 2 minus 54.15. And so we can say that the mass flow rate at inlet 2 is 14.15 kilograms per second. And now what are we trying to find? We wanted to find MI2, so we found that. We wanted to find m dot at the exit. We found that. And the last thing we want to find is the speed at inlet 2. We're given that area. Okay, so this is one of the things we were asked for. This is one of the things we're asked for. And now we can say MI2 dot is equal to 14.15. And that's equal to A times the speed divided by the specific volume. The area was 25 times 10 to the minus fourth. We're trying to calculate that speed. We know the specific, well, we can look up the specific volume. So we'll look up the specific volume for inlet 2. That is liquid water. So we're going to look it up at a pressure equal to 7 bar and a temperature equal to 40 degrees Celsius. And this gives 1.0078 times 10 to the minus third cubic meter per kilogram. And so we have 14.15 is equal to 25 times 10 to the minus fourth times the speed divided by 1.0078 times 10 to the minus third. And you get that the speed at inlet 2 is equal to 5.71 meters per second. So when you have to worry about the phases and stuff like that, be ready to look stuff up in the table. Remember that, you know, if you're at a saturation point, you only need one property to look it up. If you're not at a saturation point, you need two properties to look it up. And then it's just a matter of like stringing the right equations together to solve for the variables you need. Also, you know, in the example before, I said, let's just use specific volume of water at 0.01. You know, notice anywhere in the table, in the compressed liquid water tables where you look up a specific volume at a given temperature and pressure, you know, we took into account a specific temperature and a specific pressure, and we got basically 0.001 there, you know. It just doesn't change very much. Any questions? Okay, I'm going to remember to give you an assignment today.